This event today is the final pre-Discovery Rooms event on Wednesday, the 26th of January. It's 3 p.m. here in the UK, and we are delighted to be bringing on to the stage Atul Rana, Dr. Atul Rana, no less, who is many things, really too many to put into a title description. We've put here expert maths and science tutor because that's what is probably most applicable to today's crowd, but Atul also runs several very successful Facebook groups. He has been involved in BitPaper since the early days. He's a very active Twitter user, sharing a lot of helpful insights. And he's also a member of a band, a busking group, several busking groups, in fact. So if you find yourself in the streets and corners of East London on weekend afternoons, you'll probably see Atul playing with his fellow band members. So Atul is many things. And today we're going to be looking at algebra tiles, which is a key area of maths. By all accounts, I'm myself not a maths expert, so I will be quickly handing over to Atul. But really, algebra tiles, as a brief background, utilize the powerful area model, providing stories and hooks for learners that they explore through movement and pictures. So as Atul has laid out here, seemingly complex ideas like proof, multiplying out expressions, division methods, factorizing quadratics, completing the square become instantly accessible to all learners rather than the select few that were lucky enough to grasp these ideas in the abstract. Atul's quite right. The best way to learn maths is to play with it. You will get the opportunity in this workshop to manipulate virtual algebra tiles, much like in Judy Bryce's CPD accredited workshop this morning, making your own discoveries on how seemingly hard maths can be communicated easily, filling your tutees with confidence and adding immeasurable value to the tutoring you provide. And as we've laid out there, this workshop is suitable for both primary and secondary tutors. We can't start without thanking the lead sponsors of the Love Tutoring Festival, to Nudge Education. If you haven't heard about them yet, then they are a wonderful organization here in the UK, eradicating chronic disengagement and leading the charge for tutoring in schools. And another organization also leading the charge is Manning's Tutors, who are the sponsors of Day 3 here at the festival. And they are a key national tutoring program provider and a long-term training partner of Qualified Tutor. So that's the formal introductions done. Atul, I'm going to hand over to you now, if that's okay.
Fantastic. Thanks for the introduction, Ludo. I'll just screen share and then we'll get started. So let's get this going. Can everyone see that? Or you can see that, Ludo?
Yes.
Okay, perfect. All right, brilliant. So yes, so if you are, I'd love you to get enrolled in the chat. I've got it going up there. If you're on Twitter, take some screenshots, post away. I'm all over social media, fairly shameless with it. And there'll be a couple of breakouts, one's probably in about 15 minutes and then another one in about 35 minutes. We get to play with the things, with the virtual manipulatives, which Judy did earlier on. So I'm on Atul Rana, so you can tag me when you're on their Twitter. And again, maximum props to the Love Tutoring team. I love the fact that you call this a festival rather than a conference. Plays right into my love of live music. So for me, this is like a gig. This is a festival, and it's got this kind of organic vibe to it. So I'm going to quote one of people I've learned a lot from, Mark McCourt of LaSalle Education Complete Maths. He says, tutors are intellectuals, and we all have our own series on learning. What we do is really complex. We're doing constant experiments daily. We're tweaking things, we're changing them, and we're trying to like tune into the brain of one person and see what works and see what doesn't. And there's a lot of stuff swimming around in our head. So we really need to talk to each other, and you provided this incredible platform for us to do so. So I would say there's like 3 levels of learning or teaching when you're teaching maths, especially. When you first start out tutoring, you start teaching in the way that made you successful in maths. So for me, that would have been the way the techniques I learned for A-level maths, GCSE, etc. And then you teach a whole bunch of tutees, and you realize actually I need things that the way I see it is not the way my tutees see it. So I need more tools in my toolbox, and you gradually learn and accumulate these toolbox ideas over the years. And then the next level is this is what's happening right now. It's a CPD, and you are now learning from other teachers slash tutors. I see teachers tutors as the same thing, so I don't really see that dichotomy at all. So you're learning from other teachers in how they teach, how they impart this learning to their own students. And this is like a much higher order way of learning, because you are, so if I'm learning from another teacher or tutor who's taught for 15 years, another one for 15 years, we've got that combined experience. And I'm going to argue this has actually never happened in the entire history of tutoring until now. And Love Tutoring are making that happen. So I'm so excited. I'm so excited to learn from you, to meet with you. I learned loads from every single teacher and tutor I meet. So onwards. So onwards, the maths itself. So I'll call it rank in order of difficulty. Here's a few mathsy things. I'd like you to just, in the chat, roughly, it doesn't have to be exact, what do you think is the easiest or has the least cognitive load? So say you think this is the easiest, so you can start with 6 and just rank them roughly. So it could be, I don't know, 4, 2, 1, 3, 5, 6. And I'll wait a bit to see what appears in the chat. Okay. Doesn't have to be exact, just very roughly speaking. It's just kind of like a tutoring session. You're getting some ideas off and pinging back from your tutee. Okay, 6 is coming up top. 6, 2, 5, 4, 3, 1. I like that. I have no idea what that means. Number 3. I can reveal that complete the square literally means complete the square. You'll see that soon, and you'll be doing that yourself. Okay, brilliant. Quite a few responses. Love it. I'm going to make a rather bold claim and say that all of this requires the same amount of cognitive load, which is very little if you use the right representation. So all of this is accessible. So 143 divided by 11, let's say it's being done in year 2 or year 3. I'm going to say a year 2 or year 3 child could do proof sum of any two odd numbers is always even, which is usually considered to be the higher level topic at GCSE maths. So a bold claim, and I promise you'll be doing the same thing by the end of this session. So before all of that, what are algebra tiles? So the algebra tiles is part of the area model, and the area model has been around since the beginning of time, since the ancient Egyptians were plotting up bits of land, since we moved as a civilization from hunter-gatherers to agrarian societies where land became important. It was formalized more by Al-Khwarizmi in his book in 800, and it uses the idea of area. So here's a little yellow tile. It's a 1 by 1 tile, and it's got a length of 1 and a width of 1. So it's got an area of 1 times 1, 1 unit square. I could, hang on, I'm just going to move this screen share area up a little bit. So I have a bit paper toolbar there. Yeah, okay. So you can take this 1 by 1 tile and you can stretch it to 1 by 2, 1 by 3, 1 by 4, 1 by 5, whatever you want. I'm going to stretch it to an unknown length x. I don't know the length, so I'll just call it x. Here it's finite. It's actually 4 and a bit, but it's on purpose. I made it so that you can't fit in 4 tiles or 5 tiles. It's x. So following on from there, x copies of x multiples of x gives you another tile. called the x square tile. So these are our main tiles, the one tile, the x tile, the x square. The x tile can be in this orientation as well. Square tiles, the orientation doesn't matter because they remain a square. There are also these negative tiles, and what a negative tile does, basically 1 plus -1, when you add them, they kind of negate each other out, zero each other out. They're all part of zero pairs. So it's the same with these ones. So each tile has like its anti-tile, or Paul Lockhart calls sheep. A sheep has an anti-sheep. A sheep joins an anti-sheep and becomes zero. So tiles, anti-tiles, particles, anti-particles, generally into deep physics there. So algebra tiles are these real things, and this is an actual photo from when I was training with them 5 years ago. And I really actually encourage to use real ones as along with virtual ones. Of course, we're on a virtual platform here right now, so we will use the virtual ones, and so will you. But I do recommend getting hold of those. So those are, again, the same tiles you saw there. Brilliant. So I promise, even if you're not math specialist or you don't like maths, you'll get this immediately. Odd and even numbers. So one way of looking at odd and even numbers is just arrange them with these tiles, the one tiles, 1, 2, 3, 4, 5, 6. What do we think as evenness in language? We think of it as kind of being the same, two things being the same. So if I say I've got an even pair of socks, I've got the same color socks. So a measure of evenness, at least in this, is that you got 2 there, 2 there, 1 there, 1 there, 3, 3. So the numbers are even, and that's the definition that we can use in mathematics as well. So what's odd? Well, odd is simply you've got 2 different ones, so they're not the same. So evens and odds obviously alternate. So if you get another one there even, the next one odd, and so on and so forth. So now we can see visually what even and odd means. So this next proof is actually in GCSE. It's an algebraic proof. It's usually considered only accessible to the higher level students, but doing it visually means anyone can do it with this kind of method. So here's an even number, and here's another even number. To be honest, it doesn't really matter what it is. I know that's even, and this is even. And the idea of adding is actually one of the most fundamental ideas in mathematics. Everything else comes from it. Repeated multiplication, adding, the inverse of adding, subtracting, or adding with negatives. Division is the inverse of multiplication. So adding is almost the one that births all of them. And the initial idea of adding as a civilization and humanity was actually abstracting things with the rocks and pushing them together. So we'll just push this even number together to that even number. And it's clear if you join up 2 even numbers, any 2 even numbers, because you've got an even array, you get up another even number. So even plus even is even. Proof done. Here's an even and here's an odd. What happens when you join an even with an odd? Well, the odd's got this kind of sticky out bit and the even hasn't. All odd numbers will have a sticky out bit, all even numbers won't. So push any odd number with an even number, get an odd number. So even plus odd is odd. Here's an odd number, it's got a sticky out bit. Here's another odd number, it's got another sticky out bit. So what happens when you push those together? Well, it's not exactly clear what happens there. So what I'm going to do there is I'm just going to twist this around and sticky out bit in a different orientation, sticky out bit in a different orientation, push them together, and look at that. They fit in beautifully. So any 2 odd numbers added together, I'll just rewind that. So any 2 odd numbers when added together gives you an even number. And you can just do that with the tiles. I did this with the tiles, but you can do this with penny coins as well if your student doesn't have it. So I just set them up as penny coins as well. So this is proof, one of the most fundamental ideas in maths, and what mathematicians love to do. We like to generalize things. So we take some example cases and we say, does it work for this case, this case, this case, this case? Can we generalize it for everything, for the entire thing in the universe? Yes, we can. We can, for every single prime, even an odd number, we can generalize this. Okay. Actually, I'll just do this one here. Okay, so here's numbers as well with the tiles 1, 2, 3, 4, 5, 6. This is 7, and so on. So I also get students to do this. This can also be in penny coins, to be honest. It doesn't have to be tiles. So I'm going to call this thing roughly, can we make rectangles out of it? Or I'll just call it rectangularize. It's not a maths term. I use that with my tutees sometimes, and I'd give them the technical term later. So can we rectangularize these numbers? Well, 1's already, it is what it is. We're going to leave that alone. 2 is already a rectangle. I mean, I could make it a rectangle in that orientation, but it's still basically the same thing. Turn around. Can I rectangularize 3? Nope, no can do. 4. I can make it into this type of rectangle. Special case of rectangle, which is a square. So 4 can be rectangularized, and this gives us what looks like a square. And 4 is of course a square number, and you'd be amazed by how many tutees don't know that a square number literally means you can make a square out of it. Quite literally, you can make a square. So that's why 4 is a square number. Can I rectangularize 5? I can't. Can I rectangularize 6? Okay, we're talking now. Rectangularize it like that. I can also rectangularize it in the other orientation. Oops. And you know what's going to happen on bit paper. All right. And of course, I can have 6 in the original rectangularized format. Yeah, well spotted, Helen. Factors. Yeah, can have in that. So that's also 6 multiples of 1, or in this way. So yeah, 6 can be rectangularized in many different ways. So this gives the idea of factors and multiples, and 7 can't be rectangularized any other way than that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, see, I lost count myself there. Why did I put 9? This is for another square number. So this ties in with the whole idea of factors, primes, and multiples. So if I can't rectangularize any number other than the orientation it's prime, that's one definition. So one is prime, of course. 2 as well. 2 is the only one that's even and prime. So that's one way of just exploring. So the students have to play with this and try and rectangularize in as many orientations as they can. And I just stopped at 9, but I'll go on until 12. I think you'll be doing that later, actually. Forming expressions, distributive property. So you can use the tiles. Here's the x tile, here's 3, 1 tiles, and here is x plus 3. What if I wanted to make 2 copies? So I'll use the word copies initially, because I think that ties in beautifully with bit paper as well, or any kind of online whiteboard. You can literally select the whole thing. So I've grouped it now. Control C, Control V, copy. So I've actually made a copy. Mathematically, I made a multiple. So if this was x plus 3, this is 2 copies of the whole lot. X plus 3, this is 2 copies of x plus 3. So I've made the expression 2x plus 3. So in maths, we call this, if we go the other way around, we would call this multiplying out. So 2x plus 3 is really 2 multiples of x plus 2 multiples of 3, which is 2x plus 2 times 3 is 6. What this is mathematically, it's one of the field axioms. It's called a distributive property of addition, of multiplication over addition, which sounds a lot more complicated than it is, but it's very simple. All you're saying is if I made 2 copies of this thing, then I actually end up with 2 copies of x as well. And if I made 2 copies of 3, I ended up with 2 copies of 3. And overall, it's just 2x times plus 2 times 3. So that's just showing visually the distributive property. If I have x copies of x itself, I then end up with x squared. So I get students to do this as well. So they just make copies of this to make their own expressions. And you can go in reverse as well, which would be factorizing. which is the next one. So here I've got 2x plus 6, and I want to go in reverse. I'll just use that word again, rectangularize 2x plus 6. So there's a random 2x plus 6. I'm going to go on MathSpot. I would actually also encourage you to play around on MathSpot yourself. So let me just give you the link. I'll just put it on the chat window. So you can open that up, and let me just adjust that. Yeah. So what was I going to do? Forgot. 2x plus 6. Okay, so 2x's is 1x is 2. I'll drag 6 of those. I can also make copies of that quickly. That's 6. That's 2x. That's 6. How can I rectangularize this? I'm gonna do it this way. Just gonna snip that into bit paper. That's MathSpot. So that's 2x plus 6 rectangularized. And in this vertical direction, I have the number of multiples. So I've got 2. Yeah, I like to think of it as the number of copies. So the number of copies is going in the vertical direction. The thing that I'm copying is in the horizontal direction. So x plus 3 is what's being copied. So x plus 3 is the very thing, and that's being copied twice. So 2 is the number of copies, and x plus 3 is the thing we're copying, and everything else in between. Copying on bit paper, yes, Command C, Command V, just like the usual thing on Windows or Mac. Or on Mac, it'll be on Mac is Command C, Command V, Control C, Control V on Windows. So I can have my negative 3x plus 9. I'll do another example. Let's do that. I'm just going to tidy all this. Negative 3x. I think it was plus 9. Yep, plus 9. So I'll just do that. So negative 3x there. And then plus 9. I'm just going, yeah, let's do it this way. You can have the tiles on bit paper as well, but they don't snap. So this is the best way to do it. So I've rectangularized my negative 3x plus 9 as well. In other words, I've factorized it. So how many copies? 3 copies downwards. 3 like that. And what have I copied? Negative x plus 3. So that's factorized. So that's negative 3x plus 9 factorized using algebra tiles. I should have put this one as well. That's 2 copies of x plus 3. Okay, your turn to play. This is a hands-on activity, or in this case, virtual hands-on. Create the expression. So I've done an example here on the right-hand side. This is an example of how I would create the expression. 2 copies of x plus 3. Come up with some factor pairs of 6. So you will do that for 12. Factorize 2x plus 8. So you'd start off with 2 greens and 8 yellows and rectangularize them. So let's call this about 6 minutes, and I will pop into each breakout room. Ludo, you can make the breakout rooms. I think about 3 or 4 people should be good per breakout room, and I'll see how it's going. And hopefully this can be screen shared to all breakout rooms, but if not, I'll just put it in the chat window of what you have to do.
I'm fairly sure you can share to all breakout rooms, but if not, yeah, I can actually just take a screenshot just there.
Yeah.
And I will just pop that screenshot in the chat so that you've all got it in the chat before you even go into your breakout rooms. But I will also attempt to screen share it.
Yeah, for about the first minute or so, and then take it from there. Yeah.
Brilliant. So we've got about 6 minutes. The rooms are open. You are welcome to go into your rooms. Atul, you can Atul, how was that? How was it moseying around the rooms?
Yeah, it's great. Just good to see that people could see a way of knowing that you're really just playing with it. There's a few things I need to clarify as well. So that's great feedback on for me as well. Like especially what does factorizing 12 mean? So that just means you have 12 of those yellow bricks and you put them into a rectangle. So that could be 6 and 6 on 3 3 3 3 4 4 4 4 4, etc. So yeah, it's good. Okay, is there any question anyone else had before I move on to the next stage? Okay, I'll screen share away, and so there'll be another breakout where we'll be doing another activity soon. All right. No, that's not what you want to see. That's what you do want to see. Okay. So this is another activity which we see a lot in maths. We call like terms. So here we've got the x square, x, one tile. You can also have y tiles actually, just a different length to an x tile. So they will also produce a y square tile. One in common in both, and you can have x multiples of y and xy tile. We won't be using that one in this session. So it's very common when you see students do these kind of things. Let's say they have something like 3x plus x square plus, or even 3x plus x square. They may actually add this thing up and come up with something like either 4x square or 4x cube. So when you see this written in the abstract, and you can see why they would do it, because it's all symbolism. But when you create this with the algebra tiles, the 2x tiles are green and the x square tile is blue, and it's a totally different shape. So if you were to add the tiles together, you can't come up with something else, because that's that. So adding is aggregation. It's just pushing things together. If I push that with that, and then I push that with that, the x tiles and the negative x tiles would actually join up as like the tile and the anti-tile. It's got its evil twin, the tile and its evil twin, so that they annihilate each other to make zero. And these terms are actually used in particle, antiparticle in physics as well. So this becomes zero, and I'm just going to remove them all together. They're gone. So there's no other particle than particle than anti-tile. So has been simplified. This is a y, this is an x square, this is negative x, and then plus 1. So collecting like terms is also a really useful thing you can do with the tiles, because they are so visual and clear. And once you've done that with enough of the tiles, you can do them with pretty much any expression. So division and the area model. So division is one of the trickiest of the four operations actually. So what does it mean to divide? It means you take 143. So there's 143 here. This is a 10 by 10. These are actually Dean blocks or base 10 blocks. And algebra tiles are an evolution of these, or they come across after this. And the exchange rate here, by exchange rate I mean you can have 10 ones to make a 10, and 10 tens to make 100. So 143 divided by 11 is basically saying if I've got the area as 143, so I'll just call that the area, and this is this vertical side length. So and that's 11. So if it's 11 this way and the area is 143, the division problem in the area model is saying how long will this length be? Well, if you have your base 10 blocks and you make 143, and you make it so that you can only have 10 and 1 this way, so 11, then you will see that actually horizontally I can have 10 this way, 1 2 3, I can have 13. So 143 divided by 11 is 13. So as a like a bus stop division, you can also do that as a bus stop division. So 11 is called bus stop division because it looks like a bus stop. 143. And of course, you can go through the algorithm and work it out. And eventually, through long or short division, you'll see that it's 13. So this is taught to primary school children. And for those who don't teach maths, you'll be familiar with it. At some point, you would have done it in your lives. And the really interesting thing about this symbol is that in some countries, I had a student, Qatar, for example, who used this for the division symbol. So she would have put 143, 11, and then she would have done all it in that downwards direction. So the division symbol is like that, It can also be like this. But what all of these division symbols are all a variant of a box that says the area is 143 and this side length is 11. So the division symbol itself is the area model. It's like emulating the area model, saying this is 11 and this is 143 in area, and this quotient, the answer, is producing an 11 by 3, 11 times 3 rectangle, 143. So the very symbol comes from division, from the area model itself. We're on to some kind of GCSE A-level maths for factorizing quadratics. So factorizing quadratics, the word quad in Latin means four-sided shape. So here they are literally quads now. We've got one blue tile, got 5 green ones and 6 yellow ones. So what does factorizing mean? In maths, actually, it means just coming up it as a two expressions that multiply together to give this thing. But x squared plus 5x plus 6 is an area, and it's going to have, again, I'm going to say we're going to rectangularize it. It's going to have 2 lengths, and one of the lengths will be this factor and the other lengths will be that factor. So I'll go on to that. X squared plus 5x plus 6. I'll tidy the old one. X squared. I'm going to have 5 of these greens and 6. You can also drag them like that. So this is x squared plus 5x plus 6. I need to somehow arrange this in a rectangle. You can also turn these. There's a turn option there somewhere. Or I'm just going to delete it and get one of these instead. I'll keep this one here. So it's just movement. Obviously, I know this one, this example, so I can do it fairly quickly, but students may take quite a while before they stumble onto this, but it does exist, and they'll eventually find it. So I'll snip that over to bit paper, which is where I'm doing all the annotating. So I have rectangularized this, which means one of the side lengths is one of the factors and the other ones is the other factor. How long is this side length? Well, it's x long already and 2, so x plus 2. And this one here is x long this way and 3 along that way. It's x plus 3, so that's done. It's one of the trickiest things in GCSE maths, and using the factorizing done. So area of that made into a rectangle, one side length that, the other side length that, factorizing done. I'll do one more example. 2x squared plus 5x plus 2. So there's 2 of them. 2x squared plus 5x. So I'll put 4x's there. I'm just doing this one straight up. So this also becomes a rectangle, and I should say this is analogous to 6 being 3 times 2. So a number this pure number format 6 can be factorized in inverted commas as 3 times 2. So numbers are also factorized, they're prime factors, in the same way as this quadratic and can also be factorized by the area model. So how long is this? X plus 2. So one of the factors is clearly x plus 2. And here we got 1x, 2x, so it's 2x long plus 1. 2x plus 1. Done. And you can check this as well by multiplying it out and seeing if it works out to be that. And this one is completing the square. That's one of our trickier concepts. Completing the square is literally what it means in this context. In GCSE, you probably don't actually see any squares if you thought it'd be all in the abstract, but I'll show it to you here. X squared plus 4x plus 3. Again, tiny x squared plus 4x. So it's 1x, 2x. Put these together, so that's x squared plus 4x plus 3. So 3 means 1, 2, 3. This is nearly a square. This is a big square, which I'm going to put on bit paper and annotate. It's just missing that one yellow bit. So it is a square which's got a length of x plus 2 with this yellow bit missing, and x plus 2 that way as well. So I could say it's x plus 2 times x plus 2. So it's really an x plus 2 whole square, but it's missing one yellow thing, so I could call that minus 1. So x squared plus 4x plus 3 in complete the square form is x plus 2 whole square minus 1. All right. Your turn. So you can factorize these quadratics, and there's just a couple examples. There's also complete the square, but let's go with factorizing these quadratics. So Ludo can screenshot this, but this is one blue tile. These are greens and these are yellows. Oops. Okay, how much time we got? We got we can do a 6-minute breakout again, and I'll kind of wrap it up after that. I've got a couple of short slides after that.
We might need to keep it just to a little bit shorter because we've got the raffle prize to fit in before 4 p.m. Atul. But we'll give you about 3 or 4 minutes in these breakout rooms. So is this completing the square tile, is it, Atul?
Yeah, let's just do this one, x squared plus 6x plus 7, just the one factorizing. Yeah, I'll get rid of that one. All right.
Wonderful. Okay. Sholto, those breakout rooms ready? Real. Okay. I will be sharing screen then, and we can open those rooms.
Brilliant. See ya. Yeah. So in a few rooms, people are figuring it out.
Sorry, Australia, Melbourne, in Victoria.
Lovely. Thanks for coming.
All right. So I'll wrap it up there, and I'll wrap it up in a second. But so in a few rooms, people are figuring things out. It's all being part of mathematics. Mathematicians plotted things, struggled through it, kind of bodge their way through, discuss with other people. That's all part of mathematics. It's one of my favorite quotes by Anne Watson, and it just kind of reiterates what Julia was saying earlier, and with tutoring in general, that we've come in here to help children. No child should ever feel like they have got left behind. The curriculum is an artificial concept in some ways to get students to where they are. The age-related expectations to me mean nothing. Teach them the mathematics that they know already and build from there. It's simple as that. And I do most of my professional development through the Complete Mathematics, who are open to mathematics tutors as well. They have about 20,000 schools on their network, I believe. And my whole why is becoming mathematically literate changes a life. It really does. Understanding maths, data, statistics, and becoming mathematical is changes you for the better. So that's my why. And I'll hand over to you again, Ludo. Thanks.
Thank you so much, Atul, for jumping in there. I think that was probably can you guys hear me okay?
Yep.
Yeah, okay. That was probably the nerdiest session we've had at the festival so far, and I mean that in the best way possible. That was really in-depth, and I think that could well be the future of the Love Tutoring Festival, is these breakout subject-specific rooms where people can go into real depth. If you are into your maths, Helen Osmond will be launching the Maths Specialist Hub from the 7th of February. The first month is totally free. So Helen will drop the link in to sign up in the chat just now. But that is going to be nerding out in maths, mastermind every 2 weeks. So 2 sessions per month, and then lots and lots of discussion in between that. There's also an English hub and a science hub and a special educational needs and disabilities hub. And there's already a business of tutoring hub. So loads and loads to come from there if you like your subject specific stuff. Atul, thank you so much for joining us. It's been months and months since that I've been looking forward to getting you onto the festival. You're a wonderful speaker and you speak at some of the best events around the world. So thank you for joining us here. I'm going to close the recording.